Hey guys, I am Gautam from IIT Kharagpur and welcome to GKMX. In this video, I am going to talk about the second part of NMR series, that is about the chemical shift. Okay, so in the first part, I have discussed the basic things about the NMR, and you can see the previous video by clicking the I button. Okay, and also you will get the link in the description below. Okay, so just let's talk about the chemical shift in this video. Okay. So what is chemical shift? Actually, I want to show you it is the chemical shift by the graph. So let's take, this is a line and here you are getting a peak, right? Peak, say like this. This peak is for a reference solvent, okay, or reference sample, whatever. And if you are getting a peak right here and another peak right here, here it is NMR, that is PMR, okay. So for proton, so say this is one proton and this is for another proton, okay. So the shift, the distance between the reference and proton 1, and this is proton 2. So reference and proton 1 distance is greater and reference and proton 2 distance is lower, okay. So as the difference is greater, so we will say that the chemical shift, the difference, that is the shift, chemical shift is higher, and in this case we will say that chemical shift will be lower, okay. So this is all about the chemical shift, and let's discuss different effect, different terms, or how chemical shift term evolved, okay. So what are the bases of chemical shift? So to discuss this, let's take a system like, okay, let's take the nucleus, and around the nucleus a lot of electrons are revolving, okay. So nucleus electrons are revolving around the nucleus, okay, and these electrons, of course the negative charge species, and these electrons create their own magnetic field, okay, because of the circulation of the electron around this nucleus in the three-dimensional manner. So during circulation of those electrons, this electron creates the magnetic field around the nucleus. So if we apply the external magnetic field on this system, okay, as I have said already in my previous video, okay, so if we apply the external magnetic field, then two things may happen. First case, which we will call diamagnetic shielding, okay, and second we called paramagnetic shielding, okay. So what is diamagnetic shielding? Diamagnetic shielding means, say this is the nucleus and around it a lot of electrons are present, and those electrons create its own magnetic field, okay, and when it interacts with the externally applied magnetic field, and if those electrons don't align with the externally applied magnetic field, that is those electrons if oppose the externally applied magnetic field, okay, then we will say diamagnetic shielding is occurs. Diamagnetic means, why the term is diamagnetic is coming. And what is shield? Shield means actually electrons are shielding the nucleus to get to be resonated or to resonate when we are applying the externally applied magnetic field. What should happen? That say nucleus should be in alpha spin state, and when we apply the externally applied magnetic field along with the radio frequency region radiation, what should happen? Alpha to beta spin state conversion may occur. So these are the electrons which doesn't let the nucleus go, or let the nucleus be converted to the system like alpha to beta spin state, okay. So these electrons actually oppose the externally applied magnetic field, and these electrons don't allow the nucleus to get converted to alpha to beta spin state, okay. So here say externally applied magnetic field is in this direction, and of course the electrons will, as electrons are opposing, so electrons field will be to the opposite direction. So this is a paired up system from atomic structure, you know already, okay. So here this is paired system, and this system is called diamagnetic shielding. And why diamagnetic? Because there is no paramagnetism here, okay. And paramagnetism means the number of unpaired electrons. So the here it is paired up, so you can explain this by that in this way, that there is no single electron or unpaired electron. So here we are calling it as diamagnetic, and shielding means the electrons are shielding the nucleus from the externally applied magnetic field by creating its own magnetic field. Okay, so now coming to paramagnetic shielding. So you know about the paramagnetism, that there should be present paramagnetic unpaired electrons to show paramagnetism. So if the applied magnetic field towards itself towards this direction, and if the electrons are, I have already said that two things may happen. So I have already discussed the first thing and second case. In the second case, what may happen, that the electrons may align with the externally applied magnetic field, and if it occurs, then the nucleus, as electrons are not opposing, so nucleus can be converted to alpha to beta spin state easily. Okay, so this is called the paramagnetic shielding, because, or you may say de-shielding, because there is no shielding right here. Okay, paramagnetic shielding or de-shielding, and here it is called a diamagnetic shielding. Okay, so de-shielding or paramagnetic shielding are same. So paramagnetism means, say this is the externally applied magnetic field in this direction, and of course, as the electrons are aligning with the externally applied magnetic field, so it is also in this direction. So there is no pairing up over here. That is why it is called the paramagnetism or paramagnetic shielding, because these two electrons are unpaired, looks like unpaired electron. Okay, so that is why it is called paramagnetic shielding. So in case of diamagnetic shielding, what will be the effective magnetic field? So say externally B effective, that is effective magnetic field strength, will be, say B is the, you know about the field strength, I have considered as B. So say B is the externally applied magnetic field. As in case of diamagnetic shielding, the externally applied magnetic field is opposed by the electrons by shielding. So it will overall field strength will decrease. So it will be, that is applying minus sigma into B. Okay, here sigma is called shielding or screening constant. You know in your first year inorganic chemistry, okay, or physical chemistry courses, okay, about the shielding or screening constant. Okay, so from here the concept is coming. Okay, so in case of diamagnetic shielding, the effective field strength will be like this, and in case of paramagnetic shielding, as it is aligned with the externally applied magnetic field, so B effective will be B, and as it is aligned, so field strength will be added with B. Here the formula is like this. Okay, so I hope these 2 points are clear to you. And now I want to add something, that the diamagnetic shielding depends upon the electron density. So how? If the electron density is more, then if all the electrons can de-shield, all the electrons can shield the nucleus, and for that, if we apply the external magnetic field, then all the electrons will oppose the external magnetic field. Okay, that is thus, if the electron density is more, or more electrons are present in a system, then that particular system have the diamagnetic shielding. Okay, or the system shows diamagnetic shielding. Or say if a system doesn't have that much electron, so that system will not cannot oppose the external magnetic field. Okay, in that much, and that is why that system will not show any kind of opposing. Okay, and that easily aligned with the externally applied magnetic field. And finally, we can say that this is all about the paramagnetic shielding. Okay, so it's all about the electron density. So more electron density, that is diamagnetic shielding. Less electron density, that is no opposing is occurring. So that is why it is paramagnetic shielding can be seen over there. Okay, so now coming to next one important picture I want to I want to show you, that is about the how in a system movement of electrons are present, or movements of electrons are occurring. So say this is a nucleus, okay, and over around itself, this is the you can draw this like this, that this is the way of how electrons are revolving and creating its own magnetic field. So you just remember, I am giving the exact rotation direction. Okay, so just remember, this will be clockwise. The electron's rotation should be clockwise. Okay, and when externally applied magnetic field shows, or when we apply the external magnetic field, this kind of induced magnetic field generates, and over here the magnetic field's direction will be like this. Okay, and also like this. So what is that? Because near the nucleus the field strength will be towards opposite to the here how we are applying the external magnetic field, and near the nucleus the direction of the induced magnetic field opposes the external magnetic field. Okay, and outside the nucleus, or far away from the nucleus, this is aligned. Okay, because in this direction, here also same is true. Okay, so one thing is important, that the deshielding depends upon the electron density, as I have already told you, and the lower the electron density, the higher will be the deshielding. Okay, and finally at the close proximity, that is here close proximity of the nucleus, okay, induced magnetic field, this is induced magnetic field, this toward induced magnetic field, of course the direction is towards the below. Okay, so the induced magnetic fields at the close proximity of the nucleus opposes the externally applied magnetic field, because this is in this direction, but this is in the opposite direction, so it will oppose. Okay, because of diamagnetic shielding. In case of the nearby position, not the close proximity. Okay, so in case of this, the diamagnetic shielding will not occur, because these two are aligned. Okay, one is induced magnetic field, another is the external magnetic field. Both will align. Okay, and finally we will see here the paramagnetic shielding. So in a system we can see both the diamagnetic shielding and paramagnetic shielding or deshielding. Okay, so in the close proximity of the nucleus or near the nucleus, it will be diamagnetic shielding, and far away from the nucleus it will show the paramagnetic shielding. Okay, so now let's talk about the another point, that is how to calculate the chemical shift. So calculation of chemical shift, that is represented by delta or del. Okay, so here I will discuss two different formula. Okay, from there you can easily determine. So number one formula, and then I will explain all of this. So the magnetic field of the reference, or you can say the field strength at which the resonance of the protons of reference solvent or reference system occurs, and minus the field strength at which the resonance of the proton of the unknown, or the system for which we are determining the NMR. Okay, overall divided by the externally applied magnetic field strength. So this may be the formula, or you can add another formula, that is, you should remember both of these, because you don't know which formula you should use in your examination. Okay, so here it is about the field strength, and here we will use the frequency, energy frequency, that is unknown. For unknown, the unknown, in case of the unknown system, the frequency at which the unknown proton resonate. Okay, of course the new value will be in Hz, remember this one, hertz. Okay, and minus new value of the reference, and finally new value which we are applying. So it is applied. So remember, reference minus unknown, here unknown minus reference. So don't forget this two formula. Okay, so these two formula are the how to calculate are required for the calculation of the chemical shift. So this is the field strength at which the resonance of the photons of reference system occurs, and this is the resonance of protons of the unknown system occurs. And here unknown, here the nu is the frequency. Okay, that is in hertz. So actually there is a lot of problems solved, but I can't show you because it will make the video very lengthy. So you can check my blog. You will get the link in the description below. Over there, I will provide you the 2 or 3 or different kind of problems from this kind of formula, okay, or chemical shift formula. Okay, so they may ask questions on the chemical shift, okay, and they can also ask to solve the problems, okay, as mathematical problems on chemical shift. So you can just check the blog and you will get the link in the description below, and you can solve those questions, or solved questions you can see. Okay, so here I want to add something, that here this value is in actually hertz, okay, and this value is actually in ppm. So how to convert the interconvert the hertz to ppm? Okay, so say there is a system like you have calculated the value in is y ppm, the chemical shift value, and you want to get the value in hertz. So chemical shift in hertz, the formula is y into x. So what is x? X is the operating frequency in megahertz. So to get value in hertz, remember this one, to get the value in hertz, put the value in ppm, y is in ppm, and the operating frequency nu, that is in megahertz, okay, and 1 megahertz is equals to 10 to the power 6 hertz, okay. So this formula you should remember. So the interconversion, okay. So this is all about the basic idea about the chemical shift, and now I will be discussing the effect of different effect, and how chemical shift changes in different kind of systems, okay. So I will be discussing now in this video, and the different effects may be electronegativity effect, dilution effect, then solvent effect, okay, and many more. Okay, so first let me show you some important point or some important thing about the chemical shift. So how chemical shift looks like. Say already I have shown you, but I want to add something over here. Let's say this is 0. 0 point means the chemical shift value or chemical resonance value of the reference. So the reference proton, here we are using TMSCl, trimethyl chloride. Okay, so the proton of TMSCl generally resonates at a particular frequency or particular field strength. That is, we are taking this as a reference. Okay, and as taking it as a reference, we may get a value 1 peak or 2 peak, suppose right here, or another peak, whatever, right here. So in this direction, the field strength, the externally applied magnetic field strength generally increases. Okay, and that is why, say in a system diamagnetic shielding occurs. Okay, so if shielding occurs, then we have to apply more field strength, okay, or more externally applied magnetic field, right, and that causes the increase of field strength. Okay, and if we need to increase the field strength, then the resonance of the proton, of that particular proton of the system, will show towards right, because field strength increases in this NMR spectrum towards this. So greater field strength, lower field strength. So if we have to apply greater field strength, then we will get the NMR peak towards the right, and for other we will get towards the left. So for if in a system diamagnetic shielding occurs, then we will get the NMR peak at higher field strength, and vice versa. Okay, so if we get one peak right here and one peak right here, so we can say that chemical shift is lower right here, and that implies that this proton, okay, this proton resonates at a higher frequency or higher field strength. Okay, and because this proton is in diamagnetic shielding, but this proton is in lower diamagnetic shielding or paramagnetic shielding, and that is why it easily resonates and keep the NMR peak at lower field strength. Okay, so all clear, no problem. Okay, so now coming to the different effect or different solution effect, different effect on the chemical shift. Okay, so if you have any problem, just ask me on my Facebook group and also in the description of this video. Okay, so the first effect, the factor which controls the magnitude of the chemical shift, so the electronegativity. So how electronegativity affects? So say if a system, say CH3F, CH3Cl, CH3I, so protons are nearly equivalent. Okay, so these protons and this protons, say this is reference value. So here fluorine has the highest electronegativity, then chlorine, then iodine. So everyone will attract electrons toward itself. So if electron density shifts towards the right, then the electron density in case of the hydrogen or near the hydrogen atom will decrease. And if electron density decreases, then there will be less amount of diamagnetic shielding. The shielding is less. So if you apply low frequency, low energy or low field strength externally, of course, then easily the proton will resonate and give the NMR peak. Okay, so if electron density is less, and that will be occurred when electronegative atom attached with it, okay, more electronegative atom attached with it, then okay, due to the electronegativity, the electron density decreases and electron density will be slightly higher in this and more greater in this. So this will show the peak, of course, in low field strength. So this is the field strength order. So this will show lower field strength because of the, if we apply low externally applied magnetic field, then we will see that the hydrogen will give the NMR peak. So this will show right here, then this will show right here, and finally this will show right here. This is for fluorine, chlorine, iodine. Okay, and thus electronegativity affects the system to show the NMR peaks. Okay, so now coming to another effect, that is about the, if you just remember that, just see the position of the electronegative atom and also the electronegativity power. Okay, so by this you can easily explain all the systems. Okay, so just remember, understand this, and you can easily apply all this. So now coming to next point, that is hybridization effect. So you know about that hybridization, that is sp3, sp2 and sp. So sp3, S character is less, S character is slightly more, and S character is slightly more. This is 50%, 33%, and this is 25%. Okay, so more S character means more electronegative system. So if a system has sp hybridization, that is more electronegative, and that will attract the electron towards itself, and that causes the deshielding or paramagnetic shielding, and the electron and the system and the proton of the system will show the NMR peak at lower field strength. Okay, and thus if it shows the NMR peak at lower field strength, that is towards this, then the chemical shift will be higher. And if it shows like sp3 system, then the chemical shift will be lower, because here electronegativity is less, so electron attraction will be less. So thus it will give the final NMR peak at near the reference value. Okay, so this is the previous one. So if you want to know how sp3 and sp2 shows the electronegativity, then you can see my previous videos. Okay, so you will get the link in the by clicking this I button. Okay, so whatever, let's move on. Now coming to another point, that is resonance effect. So let's take an example, that is CH2 CH C double bond OR, and here the resonance like this may occur. Okay, like this resonance occurs. Okay, so here during the because of this resonance, the electron density on this carbon atom decreases, and that is why, and there is one plus. So as the electron density decreases, so these hydrogen, of course, the electron density on the hydrogen atom, near the hydrogen atom, also decreases, and these hydrogen, one of these hydrogen atom shows the chemical shift value at higher chemical shift value. Why? Because this is 0 field strength, higher field strength, lower to higher field strength, If the electron density is lower, then the diamagnetic shielding will be lower, and that is why we need to apply low amount of or less value of external magnetic field. Okay, so for here or here in this position, and that will give the that will resonate the proton and give the NMR peak. Okay, so that will be for resonance effect. So here in this way, resonance effect affects a system. Okay, so this is all about the resonance effect. And now coming to another point, that is dilution effect. So dilution effect is quite easy. I am just showing you why. Because this is an alcohol. So in case of very dilute solution, because of the presence of the solvent, this one molecule of this alcohol will not easily attach or will not easily touch with another molecule of alcohol. Okay, because of the solution, because of the non-polar, say non, this is a polar, but say non-polar solvent, because of that non-polar solvent. Okay, and that causes no hydrogen bonding. Okay, but if for concentration solution, if hydrogen bonding like this may occur, so okay, here this, suppose hydrogen bonding like this may occur. Okay, so if hydrogen bonding occur, then what is the condition of hydrogen bonding? Say one electronegative atom attached with hydrogen. Okay, and this hydrogen will attached with another electronegative atom. Okay, so because of this hydrogen bonding, the electron density of this is not a bond, this is just interaction. So because of this hydrogen bonding, the electron density of this bond shifts slightly towards this, and because of this the electron density decreases, and because of this decrease of the electron density, the proton will show the NMR peak at higher chemical shift value. Okay, because of this paramagnetic shielding or no diamagnetic shielding. Okay, so next coming to another point, that is most important, is magnetic anisotropy. Okay, magnetic anisotropy point is very important. Okay, so for this I just want to draw a picture. Already I have drawn it, but I just want to draw once more. And the picture is like this. Say a system, say let's take an alkene. This is alkene. Okay, so here hydrogen is present. So this is pi bond and sigma bond and pi bond is present. So electron density is more, and we will represent the system, the plane, like this. So this will be the whole sigma and pi bond plane. Okay, and externally applied magnetic field will be applied perpendicularly on this plane. Okay, so if magnetic field is applied like this, then this system will show similarly the, of course, already I have shown you that the induced magnetic field like this. So this will be towards the clockwise, and this will be near the nucleus. Here near the nucleus means here near the pi bond or pi framework system. Okay, so here it will oppose the externally applied magnetic field. So like this direction, and here it will be in this direction. Same is true for here. Okay, so for this reason, here shielding or deshielding may occur. Here shielding occur, and here deshielding, that is no kind of shielding. So shielding means these electrons, the electrons will oppose the externally applied magnetic field, and that is why that the NMR peak will show at higher at lower chemical shift value or higher externally applied magnetic field value. Okay, higher field strength value. And for here, if protons present right here, then this, in this case, that will align with the externally applied magnetic field. Okay, and that will give the NMR peak at lower chemical shift value or higher field strength value. Okay, so in case of course we are considering alkene, so protons are present nearly the paramagnetic shielding cases. Okay, so that is why protons are present in the deshielding region. Okay, so because of this, proton will show in case of alkene the lower field strength value or higher chemical shift value, because it will show the peak right here. This is reference. Okay, so in case of alkene, these kind of systems are present. Also same is true for aldehyde. So aldehyde means C double bond O and say one is hydrogen, another may be R. So here is the pi framework. This kind of induced magnetic field mesh you can show. So this will be clockwise, this will be towards right this, and this will be towards right this. So each is present towards near this. Okay, so here alignment will occur with the externally applied magnetic field, and that will give the proton, that will force the proton to show peak at high chemical shift value. Okay, because this proton is deshielded already. Okay, because of this paramagnetic shielding or deshielding. Okay, so now coming to another compound, that is about the aromatic compound. So how benzene ring affects the chemical shift. Okay, so benzene ring means a total ring system. Okay, and here there resonance of pi bond occurs, and that will provide the ring current, which is called ring current. So ring current means quite easy, it's the circulation of this pi electron. So circulation will be as always as usual clockwise, and here also same kind of deshielding occurs or magnetic induced occurs. Okay, and this will be the same near the nucleus, near the system, near the framework. It will oppose the external applied magnetic field, and in the far away of the framework, it will align with the externally applied magnetic field. Okay, so that is why the whole system, the hydrogen atom is right here, every proton is right here. Okay, so we are considering only this and this hydrogen. Okay, so here the electric field is diamagnetic. Okay, that is here it is opposing and here it is aligning. Okay, so thus we can say that here this proton feels the diamagnetic shielding, and that is why this proton will keep the chemical shift far away from the reference one. Okay, and that the chemical shift is higher for benzene protons. Okay, and the last one is alkyne. So finally coming to the alkyne region. So alkyne, you have to write the system, represent the system right like this. You cannot draw the system like this and just draw this as a framework of the system and then this too. It is not correct in case of alkyne. So this is an exception. So you have to remember this one. And for this, the shielding will be like this as usual, the clockwise rotation. Okay, and another induction of the electric externally applied magnetic field will be like this, and this will be of course like this near the system. It will oppose, and far away from the system it will align. Okay, so this will be the whole system in case of alkyne. So that is why these hydrogens are present in case of the near the this is the direction of the externally applied magnetic field, and these hydrogens present near the opposing center. Okay, because here the externally applied magnetic field is opposed by the this current or this induced magnetic field. Okay, so that is why this proton is in the shielding region. Okay, and that is why this shielding causes the chemical shift, because to resonate this proton you have to apply more and more magnetic field. Okay, that will cause the more and more magnetic field, that will give the chemical shift value very less. Okay, because this distance will be very low. Okay, so this is the in case of alkyne, So this is all about the today's video, and in the next video you will get another thing. This is not over. Okay, so you will get another video on NMR. Okay, so you may get 1 or 2 or maximum maybe 3 videos on NMR. Okay, so just keep watching, keep following, and thanks for watching.